Okay. So one thing before we get back to ramps, the first problem set is due Wednesday. So next class, at class time, 1 o'clock. Don't aim at 1 o'clock. It's a deadline, it's not a target. So before 1 o'clock, I get letters from people. I submitted at 1:01. Is it full credit? No, 1:01's the deadline. All right? Any questions about the homework, the first problem set? Okay. So where I left off last time in talking about ramps is I'd gotten as far as a wagon sitting on a sidewalk is motionless and stays motionless, or can be. And what that's telling us is that the net force on it's 0. The main thing is that it's not accelerating. Net force on it's 0, and that comes about because the sidewalk figures out just how hard to push up on the wagon to perfectly support its weight. I then tilted the sidewalk to make a ramp and showed you that the cancellation fails at that point. Let me look for 1 second, well, a few more than 1 second, at the wagon sitting on the sidewalk, that it's perfectly supported. It's easy to see that is the case. There is the question of how does the sidewalk know how hard to push up on the wagon? Because yes, it's perfectly supporting the wagon is not accelerating, but why did the wagon figure out to push it up? And this is something we pursue more last, the fall semester than the spring semester, but just to point out that there actually is a period in landing the wagon on the sidewalk when the sidewalk doesn't know how hard to push up. And the wagon is actually bouncing up and down a little bit. Believe it or not, sidewalks are not perfectly stiff. The old is immovable force, irresistible force, immovable objects. There are no objects in nature that are truly immovable, that when you push on them as hard as possible, that doesn't have a consequence on them. They do, for example, they begin to accelerate if nothing's holding them in place. I mean, even the earth accelerates if nothing's holding it in place. You push on it. If it is held in place, the object will dent. It'll deform somewhat. And so as I land the wagon on the sidewalk, that surface, which in this case is wood, and it might be cement, whatever, it could be diamond if you had a very expensive sidewalk. It would actually deform slightly downward as it acts to summon up the supporting force. The support force actually needs some deformation to appear. And so there was a brief bouncing process, at which point the sidewalk said, well, maybe I'll push a little too hard, in which case the wagon accelerates upward and begins to rise pretty soon. And the sidewalk says, oh, evidently I pushed too hard, the wagon's leaving, so I'll push less hard. And it bounced up down. I can show you that bouncing process with a very soft, bouncy sidewalk. When I put the wagon on the sidewalk, that bouncing that you see there, before it figures out exactly how hard to push up, that bouncing's real. It's actually always happening. You just may not notice it. Okay? I'll leave that notion then, and then just go on to what? Okay, so we tip the sidewalk. Once we tip the sidewalk, the wagon, if the only thing acting on is gravity and the sidewalk, the wagon's in trouble. It can't find, there is no way it can have zero net force on it. The negotiation still happens between the wagon and the tilted, the ramp. As I first put the wagon on the ramp, there's that negotiation still occurs so that the ramp and wagon don't occupy the same space. They're just dented just right to push on each other just right. But there's a leftover force. And that leftover force comes about because the weight is straight down still, toward the center of the earth. In fact, that defines, toward the center of the earth is and gravity define what we consider to be straight down. Obviously, straight down here is different from straight down in China, because the Earth's center is at a different location, relatively speaking. Anyhow, so the weight is straight down toward the center of the earth, and Now the support force from that ramp is no longer straight up. It is at right angles to the surface, perpendicular to the surface, but that's up and to the left. And as a result, those two forces can never cancel. There's no amount of force you can exert up and to the left that will cancel a straight down force. And the leftover, when you take those two forces together, considering their direction, the leftover points exactly downhill, which is itself a sort of intriguing story, but I won't do it. It's downhill and it's weak. It's weak in proportion to how shallow the ramp is. That is the less steep. I use the word shallow, which is the best word I can think of. If you got a better word, you know, it's a little late in my career, but I'd be happy to use a better word. But anyhow, if the ramp gets shallower and shallower, the force downhill, that ramp force, is weaker and weaker until finally it goes to zero if the ramp isn't a ramp at all, but just horizontal. And I will use the term ramp force from time to time, probably the rest of the semester. It's not a fundamental new force like gravity is a new force, right? Or support force is a new idea of force. It's ramp force in this case is just maybe it's even jargon. It's something to call this imperfect cancellation between a support force up and to the left and weight straight down. So that's the net force on this wagon when I let go of it. If I'm involved, I'm contributing to the net force, so all bets are off. But now, the net force on that wagon is downhill, the ramp force. And it accelerates as a result. And the acceleration is downhill, because that's the direction of the force, and it's less in amount than the famous acceleration due to gravity. The acceleration due to gravity does show up if the ramp is perfectly steep. Now, the net force on the ramp force on the wagon is the wagon's weight, and its acceleration is the acceleration due to gravity. And everywhere else, the net force is less than the wagon's weight, and the acceleration is weaker, slower than the acceleration due to gravity. Okay? What else do I want to do with this? Okay. Well, let me ask you one of these questions. The clicker question here. And if I can remember which one do I want to do? Okay, this and that. Yeah. Dun, dun, dun. Okay. Again, if you've got a clicker, great. If you don't have a clicker, great. Just the main thing is to be involved with the thinking about this, because that's where you're going to learn it. So if I push up on the wagon just hard enough to cancel the downhill ramp force, so get me involved in it now. It's a third individual force, and you really can think of I'm involved and the ramp force, because the ramp force is the sum of the other two forces. If I push up just enough to balance that ramp force, the wagon will do what? You okay with the question? Any questions about the question? All right, let's see what you think. And again, talk about this one. Yeah, get it right. And yeah. This one you all ought to be able to do, so that the fact that it's still got a large number of you do not have the correct answer means suffer over it a little bit. I will go to the 60-second point. Mm-hmm. 5, 4, 3, 2, 1, clickety, and dun, dun. D is really out there. A majority are going for have a constant velocity, which might be 0, but there are a good number of people saying that it must be motionless. What is the strongest statement you can make about the what strongest statement? The wagon is experiencing what overall force? What net force? You tell me, or at least think it. If I'm pushing up with a force just enough to cancel the downhill ramp force? What's the net force on the wagon? Zero. What do things with zero net force do? What's in this case, what's the strongest thing you can say about an object that's experiencing zero net force? That's all I tell you about it. The kangaroo is experiencing zero net force. Is it motionless? We don't know. Could be. We know about what's its velocity, though. It's not zero necessarily, which would be, but it's a choice. No, and necessarily, do say the answers. I mean, there are no stupid questions. There are no stupid answers. It's all a learning process, okay? So the strongest thing we can say is we know the velocity is constant, whatever it was. If it was zero, it's still a zero. It's going to be zero all day. If it was not zero, it's going to be that same value on and on. Is that okay? So the answer to this one is, and I guess I could ask you it again, but I'll just I'll tell you the answer at this point. It's the most we can say about it is it's got constant velocity, which could be zero, but doesn't have to be zero. Is that okay? So as much as it seems intuitively, you think, well, boy, if you push just hard enough for it to cancel its weight, well, in this case, the ramp force, it's got to be motionless. Well, oddly enough, that's not the only possibility. The other possibility is it's doing this. I'm, again, just perfectly canceling the downhill ramp force. So I can bring you another question. It's there. Too many buttons. To keep the wagon coasting uphill at constant velocity, how hard must I push it uphill? You okay with the question? So this could be a wagon, it could be a grocery cart, could be a bicycle, could be a car, all those things. This applies to all those situations. How hard do you have to push it to keep it moving uphill at constant velocity? All right, I'll call it at the minute, and then we'll take a look at the answers. We'll take a look at the choices. 5, 4, 3, 2, 1, 0. So we got a split again, which is interesting. So a majority are going for the uphill forces equal in amount to the downhill ramp force, but there are also people saying that the uphill force has to be greater than the downhill ramp force. And both of those have sort of intuitive merit, but only one of them is right. So in order for the wagon to be coasting uphill at constant velocity, what does the net force on it have to be? 0. So try this one again. See what you think here. Talk about this one. If you're at all uncertain, if what I said, what we just said, the net force has to be 0, doesn't resonate with you, doesn't mean anything, talk about it. How is it going to go up? So I got a question. How is it going to go uphill if the net force is 0? If the net force is 0, what does it do? Moves at constant velocity. It moves according to inertia. If something's heading uphill and it's got inertia dominating its motion, what's it going to do? Keep moving uphill. All right, we'll go to the 5 second more to the 60-second point. 3, 2, 1, 0. You got it. If to keep it going uphill, and this is counterintuitive too, so this is good. This is that you all sort of dealt with this one. To keep something moving in any direction, uphill, straight up, horizontally, whatever all it needs is constant, all it needs is zero net force, and it will move at constant velocity. If it was already moving, it will keep going. So where the counterintuitive part of this is, to my mind, is you think that, boy, if it's going uphill and I'm pushing it, I must be somehow overcoming something. That the downhill ramp force is pushing down. I must be swamping that. I must be pushing harder than it is. So this is your gut feeling is, think about that though. If you're pushing up harder than the ramp force is pushing down, the net force is uphill. It's going to accelerate uphill. Amazingly enough, I mean, pushing up equal to the downhill ramp force is good enough. That's all you got to do to get it to exhibit inertia, so that it simply does what it was doing. Whatever it was motionless, it'll stay there. If it was going uphill, it'll keep going uphill. And if it was going downhill, it'll keep going downhill. You don't need to overwhelm that downhill ramp force to get the thing to move uphill. You just have to balance it. That's all you got to do. If you do overwhelm it, it will accelerate. And this is true not only in the case of going up a ramp, where it just seems like you got to go hard, you got to overwhelm something. It's the same with friction. That if I take this chair, and the story hasn't started yet. Let me get the story started. Typical. Okay. I'm now pushing on it with a force that exactly balances the frictional force. And the consequence is it's moving inertially. It's got zero net force on it, or it had. The story ended. I should have told you it ended. I deliberately started the story after I got the chair moving. So once I got it moving, that's a different part of, it's a different story. Once I got it moving, it'll coast for free if nothing's pushing on it. All I have to do is balance away the net force. Again, it took 2,000 years for people. Maybe they were thinking about it before Aristotle and the Greeks, but through that whole period, the Greeks and to some extent the Romans, but mostly the Greeks, they knew an awful lot of science, but they didn't get everything right. And so this is one of these ones they didn't really understand inertia. And so it took some pretty clever people in the Renaissance era and beyond to figure out, oh, if you don't push on stuff, it keeps going doing what it was doing. Okay, so you're all right with the idea that you can push a wagon up the hill at constant velocity just by balancing the downhill ramp force. That does bring up, we're talking about the starting and stopping. Remember, I started my story after I'd already gotten that chair going. I'll let the chair sit there and take a time out. To get the wagon moving uphill for the first time. So here's the wagon. To get it, it's right now it's motionless. To get it moving, how hard do I have to push it uphill? So that's the next question to look at. See what you think. I'll go 5 more seconds. 3, 2, 1, 0. This may be a first. Oh, no, some people showed up at B. All right. It wasn't exactly 0. I should have just called it spontaneously out of the middle of nowhere. All right. So it is D. The answer is D. That if you want to start it uphill, that is to go from motionless to moving uphill, it's got to accelerate in between those two moments. So you've got to give it a net force, and the net force has to be uphill to get it started. So when you're pushing a wagon or something like that, a grocery cart up a hill, as you're starting out with it not moving, you gotta now, okay, for once you do have to exceed the downhill force. Push up harder. Yeah?
Is there a moment where you transition from the necessary acceleration to inertia? Where does that
Is there a moment when you transition from the necessary acceleration to inertia? You do this and you do it naturally, you don't really even notice you're doing it. That there's a point where you push extra hard and then you drop off and you let it go at its constant velocity. So as you do this sometime, when you're pushing something up a hill, and there are 1,000 opportunities to do this, watch yourself do that. You give it an initial shove and then you back off. Is it a single moment in time? We're kind of messy in how we do our acceleration, so I wouldn't count on it. But there is a point at which you stop pushing extra hard. Other questions? Well, the other obvious question to ask, the same idea, is how about stopping the wagon from moving? So you started it uphill, and then you coast it for a while, and then you get to the top of the hill, and it's time to bring the wagon or the shopping cart to motionlessness. Well, how do you do it? This is one of these, it's a slightly imperfect question in that E says both A and C are correct choices, so that A and C by themselves are sort of subset of E. I decided not to get too super wordy and write it all out in detail. All right, 5, 4, 3, 2, 1, 0. Dun, dun, dun. E is the best choice. Yeah, so A and C individually are okay. E is the best. And what's the idea here? That if it was going uphill and you keep balancing that downhill ramp force perfectly, it'll keep going uphill forever. But you don't want that. You actually want to slow it down. So you want the ramp force to win. You actually allow the ramp force to slow down the cart or the wagon. And you do that by just not pushing up hard enough to cancel it. You either can keep pushing up just a little bit, and it will slow down gradually, or you can just stop. Stop pushing it, and it will not coast to a stop. It will decelerate because the ramp force just sucks the forward motion out of it. In fact, it sucks the forward momentum out of it, but we haven't gotten there yet. Okay, so watch yourself doing this. You don't have to do it on a ramp. If the story is about the ramp force, yes, you do have to do it on a ramp. But if the story is about other forces that are in some ways equivalent to the ramp force, like friction, you can just do it dragging stuff around. If I just, the chair is too noisy. Friction will always fight relative motion, which we'll come to very soon. But if I want to keep this block moving against the force of friction, I have to just cancel the force of friction. So I'm going to come toward you. It means I'm going to have a short story here. But to get it started, I have to push harder than friction pushes back. So, okay, briefly made it accelerate. So that was an extra big shove to start. And now I'm just canceling friction. And now I let friction do the stopping. So you surely have memories that you can summon up of trying to drag the couch across the room. You have to pull extra hard initially to get it to moving. Not only do you have to equal frictional forces, you have to actually exceed them. So you get them moving, and then you just drag it, constant velocity, just balancing friction, and then you let go, and it skids to a stop. Okay? So that's all the story I wanted to tell, I think, about the ramp forces. themselves now take a slightly different look at the same idea. So we talked about ramps and just sort of the forces and movement along the ramp. And I could go on to the motion down the ramp, but it's very similar to motion up the ramp. At this point, you ought to be able to figure it out yourself. But what about the act of going up a ramp, and to what extent steepness matters, and the length of the ramp matters, and all that stuff? So a different angle on ramps is, it's a very wordy question, okay? You're going to pull a wagon full of kids up a hill. So you're going to start down here, and there's the top of the hill, way up there. Oh no. You've got two ways to get there. One of them is a steep slope, for example, right up the hill. And it's short. That is, if you take a tape measure out and measure it, it's a short tape measure. On the other hand, you can also take this more bending, arcing path that will get you up there, but that path is twice as long. If you measure out the length, your ruler, your tape measure is going to be twice as long. And so the question is, how much harder will you have to push the wagon along the steep path compared to along the shallow path that's twice as long? You okay with the question? And if this seems like off the wall and how in the world would you ever answer it, that's okay. See what you think. Now, of course, I should dim the light so you can see it better. All right, well, I'll go to 45 seconds and then call it, because the answers are all over. 3, 2, 1, 0. So I mean, the strongest answers are twice as hard is the strongest answer, which I guess I'll tell you, that's actually going to be the right answer. A, being equally hard, is also obviously a lot of people went for. At this point, nothing I've told you would give you sort of enough information to answer the question. So that's why I said, give it a shot, but there's no reason you can answer it yet, unless, of course, you've read the book. All right. How in the world, where does that come from? The path is twice as long. You only push half as hard. How that seems like an interesting relationship, but why? Okay, so here's the why. The why is that when you lift the wagon up this hill, and you're going to go on slopes, so the idea of lifting might seem a little foreign, but there is a lifting process. You are giving to that wagon a physical quantity that I haven't named explicitly before, that is a special type of physical quantity. It's known as, to physicists, it's known as a conserved quantity. And conserved quantities in physics and in mathematics, they're different from sort of, conservation and the sort of, we talk about conserving nature and stuff like that. No, but a conserved quantity in physics means it's a special kind of quantity that the total amount of that in an isolated system, the total amount of that quantity cannot change. You can't destroy it or create more of it. So if you've got a certain amount of that quantity, you've got it forever. The only way you can change your local amount of a conserved quantity is to give it to somewhere else. So it can move around, but it can't be just willy-nilly created. And just to give you an analogy for a conserved quantity, let's see, approximately in our normal social world is money. If you're a law-abiding citizen normally, and not a nutcase also, typically you don't create money. You go to jail for that, and you don't destroy money. You go to the somewhere else if you sit there burning money all day. So it moves around, but it's basically there's a certain amount of it in an isolated system. In physics, it's totally the law, man. You can't get rid of this quantity or make more. The quantity I have in mind is called energy. And so this is the real energy, which is used somewhat correctly in common language, although there are all kinds of other variations on energy, like, wow, I've got lots of energy today, right? Or not much. And so what is energy? What is it? It is a conserved quantity in nature, absolutely conserved, nothing you can do about it. The amount you have is the amount you will always have unless you get some from somewhere else or give it to somewhere else. What does it do for you? The amount of energy you have is it measures finally the amount of what's called work you can do. So I consider energy the conserved quantity of doing, of getting things done. And the way you do things is by a physical process known as work. So another definition for work, and this is, again, the physicist's version of work. The definition of work is it's the mechanical means for transferring energy, which is terribly circuitous. So energy is your capacity to do work, and work is the mechanical means of transferring energy from one place to the other. Well, at some point I've got to get down to brass tacks and actually tell you what one of them is. To do work, that is to give something energy, there's a very simple recipe, and it's a minimalist, microscopic recipe. That is, it's very specific and very narrow. All of the other details don't matter. To do work on this bowling ball, and it's always been this bowling ball for a long time, but somehow the bowling ball has gotten heavier and heavier. To do work on the bowling ball, which is to say to give it energy mechanically, I have to push on it with a force, and I am. And if you were me, you would know you're pushing on it. And obviously, I'm pushing up. And it has to move a distance in the direction of my force. So I have to push on it. In this case, I'm pushing up. And it has to move a distance in the direction of my force, namely up. So I just did work on it. And in doing that work on the bowling ball, I transferred energy to it. It now is able to do things by way of work that it couldn't do before, and you sort of have a gut feeling that that's the case. It's obviously more dangerous, certainly to me, maybe even to you guys, in this situation than it was to this. It's able to do more now than it could before. So I really did give it energy. And because energy is a conserved quantity, I lost the energy. That is, I gave it a certain amount of energy, and that energy came out of me and is gone. All right? So, next thoughts on that. So, to do work on something, you've got to push on it. It's got to move a distance, direction, force. Right now, I'm pushing on it still. It's not moving, though. So I'm doing no work on it. I'm giving it no new energy. And that sort of makes sense, too, because it's here able to do a certain, the variety of things it can do hasn't changed between now and now. Nothing about it changed. So it turns out that the amount of energy something's got often, is it always? It's situation dependent. So regardless of even if you don't see me doing the work, if you look now and see the ball at this height, and now you close your eyes and you look again and you see it like this, you know that the ball's energy changed because it's now in a different situation. You can assess the situation, and you actually can, in principle, figure out how much energy it's got, and it's got more than it used to. The question might come about, so where did it get the energy from? In this case, because you didn't blink, you know it came from me, but it could just as easily have been, I could have been like this, and then other people could have run in here, lifted it up there, and let me reach my hand up. The Hollywood version, like I look as though I was the hero, but actually I cheated. Okay, so energy is a state-dependent quantity. You can look at a situation and in principle figure out how much energy is there. You can also watch the energy being transferred. Either one is a good way of dealing with the energy. Just as an aside about energy, the only reason it's an interesting quantity because it's constructed out of things like forces and velocities and assessing the total energy in something, you've got to look at a variety of its characteristics in the situation it's in. It's hard work. Why would you do this? It's because energy is conserved. The fact that it's a conserved quantity makes it fundamentally interesting because you can then watch the energy move around between things. And we'll do this the rest of the semester, and hopefully you'll do this, in principle, the rest of your life. You'll watch energy move through things, and following that path tells you a lot about the things. Just as following money moving through things. The only reason money is interesting is because it's, in principle, conserved. If people could just print money in their basements any old time, we wouldn't care about it very much. I remember my son at age, was it 2 or something like that, talking about money. He's like, just go to the bank and get more. It's like you can just effectively print it. All right, so. More about energy. I've told you that to do work, I have to exert a force on it, and I have to move it in the direction of the force. What if I lower the ball? As I lower the ball, and I do it essentially at constant velocity, we've already talked about movement at constant velocity, all I have to do is balance the weight of the ball, right? As I start, things are a little complicated, but once I'm going, I'm pushing up with a force equal amount to the ball's weight. It's got a net force 0, down it comes, and then at the end I stop it. So as I'm lowering the ball, I am pushing up on it with a force equal to or very close to its weight. So it's upward force, and yet the ball is moving downward the wrong way. Well, how do physicists deal with that? The amount of work I did on it, one could say I did work on it, but it was a negative amount of work. I sucked the energy out of it. I gave it less than no energy. So this is energy into the ball. This is energy out of the ball. And you can see that from the perspective of the change in the state of the ball. It went from being a state in which it could do a lot to a state in which it couldn't do much anymore. So I evidently took away some of its energy. I did, the way we refer to it as a physicist and in the future in this class is as doing negative work on something. So this is positive work on it. This is negative work on it. And as a convention, it's not necessary to say positive work. This is work. This is negative work. We use the word negative only in the context where you're doing less than no work. When you're pushing it and it's moving the wrong way, in the direction opposite the force. And that's a convention that you're familiar with too. My joke about this is when you give money to charity, we assume you gave positive money to charity. You might wonder, can you give negative money to anything? Sure you can. Give them your mortgage, your credit card debt. Here you go, goodwill, great, here's my credit card debt. Hopefully you can understand that in doing that, giving away your debt, you actually become wealthier and they become poorer. So, by convention, we don't have to say positive. That's work, that's negative work. Is that okay? How about this? Let me get started. The story hasn't started yet, now it's going. Am I doing work on the ball right now? I'm pushing it. I'll end the story and then I'll talk. Which way am I pushing it when I was walking like that? Straight up, right? I'm simply supporting its weight. It's moving at constant velocity. And it's moving horizontally. Ooh, those are at right angles. So you're okay with the idea? I'm pushing it straight up, but it's moving perpendicular to my push. In that case, I'm doing zero work on it. No work at all, because it's not moving in the direction of my force or opposite the direction of my force. It's a nothing. And that's consistent with the state picture of things. So as I'm going, let me get started again. Not yet, now. At this point, I'm pushing it straight up. It's moving horizontally. its state isn't changing. It's got the same energy now as now, and I better stop the story. So it's not able to do more or do less. Nothing's happening. So as you're walking along with your backpack, just merrily along a horizontal path, you're not doing any work on it. To the extent you're not speeding up or slowing down. If you're speeding up or slowing down, life gets complicated. But if you're going at constant velocity, essentially, you're not doing any work on it. Okay? So, I'll ask this question. You're having fun next door. It's quite a... Okay. So to go from the first floor to the second floor of some, I don't know, some fancy store, you can take the elevator or the escalator. And hopefully you all know what an escalator is, right? It's one of these moving staircases at an angle. And your starting point and finishing point are the same in either case. So you're going to start standing where, right here, and you're going to end the floor up right there. And you go from motionless to motionless to make life very simple. And so which of these devices does more work on you? And taking you from the first floor to the second floor. You okay with the question? Well, I'll call it a day here. 5 seconds. 4, 3, 2, 1, 0. Okay, so it's a split between A and C. The actual answer is it's going to be C. And so some of this is new, because we're developing as we're going along. So I'm asking you questions a little ahead of what I've told you. It's the elevator. People are thinking might well do more work on you. It's actually a sort of a sophisticated issue here that when you're going on both the elevator and the escalator, and we're going to have you do it at constant velocity, which is typically what you do in an elevator. The elevator does have a brief starting period and a brief stopping period, just like the cart going up the grocery cart or wagon going up the hill. Same with the escalator. But most of the time in an elevator and most of the time in an escalator, you're traveling at constant velocity. In which case, the surface you're standing on in both places, elevator, escalator, is pushing you in which direction? Show me with your hands. Straight up. It's just supporting your weight. You're coasting otherwise. So the escalator and the elevator are pushing you straight up with a force equal to your weight. They're exerting the same force on you, straight up. Except at the very start and very stop, which finally the details there turn out not to matter. So they're both pushing up on you with equal pushes. The issue now is how far do you travel in the direction of the force, namely straight up. The elevator, it's very clear. You travel, because it moves straight up. So it's easy to go the distance you travel and the force, which is your weight, just multiply them. And when you do that, you get the unit you get is a force times a distance. For example, foot, pound. Well, that's back from pound, foot. Foot, pound is the American imperial unit of energy and work. In the metric system, it's the Newton times the meter. So it's the Newton meter is the unit of work or energy. Newton meter is so important in physics, it's given its own name. It's called a joule. And joule of energy is the standard unit of energy. I'm not going to worry about the units for the moment, but rather that on both of these lifting machines, the force is straight up. The distance you travel upward in the direction of the force is the same. You go from the first floor to the second floor. The escalator, it takes you at a cockeyed angle, but the cockeyed part doesn't matter. It's just the up part that matters, the distance in the direction of the force. And as a result, they do the same work on you. The fact that you go sideways to some extent on the escalator is irrelevant. You get the same amount of work put into you. And that makes sense because you end up in the same situation when the dust settles. At the end, you're on the second floor as opposed to the first floor. You have more energy in you. The energy you have in you is in the form of what's known as gravitational potential energy, or you may have heard of it just simply with the word, just without the word gravitational, just potential energy. I put gravitational in because to point out that it's an energy that is stored. Gravitational potential energy. It's energy stored in forces, in this case, the force of gravity. Yeah? If something does more work on you, that means it exerts more force on you. Or you travel more distance, or both. And so, thanks for asking that question. Actually, there's a question that I'll come back to next time that came up here. What I wanted to finish with on this is go back to this. Remember this question? I asked you this, and this one was a toughie because I hadn't given you enough information to answer this one. If you go up that hill from down here to up there, you go by the steep path or you go by the shallow path, you're going to do the same work either way. How do I know that? Because work is state dependent. If you go from this location to the top of the hill location, we know that a certain amount of work was done to get you there. You've changed energy. You have a certain energy down here. You have a certain energy up there. It's more. You have more gravitational potential energy up there, and I still need to pin down what the potential. Again, potential energy is energy stored in forces. In this case, the attractive forces of gravity. To get you higher, we have to pull you away from the Earth, farther from the center. We're kind of like stretching a spring. It's not quite like a spring, but it's, that's the sort of idea. We've packed the system full of the ability to do stuff, specifically to do work. So lifting you up there packed you full of work, full of energy. In any case, this question says that if you go from down here to up there, you're going to have received a certain amount of extra energy. And it's going to have appeared by way of, in this story, of you doing work on a bunch of children, dragging them up a hill. If you take twice as far to get them up to the top of the hill, which you do on the shallower slope, you're using less, you've got a longer distance over which to do the work. As a result, you will do it with a smaller force. And in fact, you've got twice the distance to travel, you'll do it with half the force. And so that's related to the question that came a minute ago is when doing the work of, for example, lifting something from this location to that location, you can do that lifting with a large force exerted over a small distance, which I just did, or with a small force exerted over a very long distance. The product of the two, the force times the distance you travel in the direction of that force, will stay the same because you went from a certain energy to a certain higher energy. And that makes the answer to this question possible. If the path was twice as long on the shallow slope, you'll do it with half the force. And that's a notion often called mechanical advantage. You all learned in K through 12 about simple machines, levers and inclined planes and all those things. What most of the simple machines do for you is they allow you to do the work that you have in mind. For example, lifting something from here to there. You can do the work with a different pairing of force and distance. You can reduce the force you have to exert on something with a wrench, for example, or pliers. But to pay for that, using less force, you have to go longer distance. You have to exert the force for longer distance. So, okay, I left it a little incomplete, but we'll pick it up then on, what is it, Wednesdays next.